Okay, so welcome to the third lecture on surface integrals. So last time what we talked about was we talked about integrals of this form, right? So it's a scalar valued function, a scalar field, and what you're doing is you're integrating with respect to this arc length element. Sorry, not arc length. I'm sorry, the surface element ds. That's a scalar quantity. But what I'm going to do here is I'm going to now define a vector surface element. Yeah, so notice that this is ds with a line under it. How am I going to define it? Well, my surface element was just this element over here, and I thought of that as a scalar quantity. It's just going to be the area of that small quantity. But the point is that when I have a surface in three-dimensional space, the surface is going to be curving in different directions. So the normal vector is going to be changing. So let me write down a normal vector to this, and I'm going to call it n. And I'm thinking of this as a unit vector. So usually if I put a hat on top of it, that's an indication that this is a unit vector. So I'm thinking of drawing a unit vector pointing perpendicular to this surface. So what I mean by that is that if I have just a tiny line element which lies on the surface, any line element which lies on the surface from this point, it's going to be perpendicular to this. Rather than just having a surface element, which is just a scalar quantity, I'm now defining a vector quantity, and I'm constructing this by having, well, the size of this is given by the surface element. So that's just going to be the area, but then the vectorial part of it, which is the directional part of it, is given by the unit vector, which is perpendicular to the surface. Okay, so I'm going to define this to be the vector surface element. And why is this going to be important? Well, it's going to be important in something called a flux integral. And what I want to do is just give a motivation as to this. So suppose you've got water which is flowing in this direction, right? So it's just flowing like this with a velocity u. Let's suppose that's a constant, and we want to find the flux across an infinitesimal area. Right. So what I have here is, think of this as actually a little sort of a picture frame, if you will, right? So I have this little picture frame, just the outer frame of the picture. And what I'm trying to do is I'm trying to figure out the amount of water which flows through this. So it comes like this and it flows through this. So this is sort of I'm trying to draw this in 3 dimensions. So there's a depth here as well, but part of the water is going to flow through the picture frame, right? Well, so what does the flux mean? The flux means the volume per unit time that flows through this, right? So this would be in, say, liters per second or something like that, if I'm thinking of this in dimensional units. So that's what I want to do, right? So it's the amount of water which is flowing through this. Of course, even though now I'm thinking of this as a picture frame, in general, you can just think of this as an imaginary picture frame, something which doesn't actually exist there. And you can still calculate the flux which is going across that. Okay, so what I'm now doing is, so my picture frame, this is just one side of the picture frame. The rest of the picture frame goes downwards into the page over here, and I'm trying to calculate the flux which goes across this. Well, in order to calculate the flux which goes across this, what I'm first going to do is I'm going to draw this little construction. I'm going to draw a line over here, which is sort of like a picture frame in and of itself over here. So that also has a certain depth to that. So I can't see the third dimension, the other dimension of the picture frame, right? So it's something like that, but I can't actually see it the way that I'm drawing it like this. And what I realize is that whatever flows through this is what flows through this, right? So so the flux through the surface that I want, the picture frame that I want is going to be given by the flux which is through this thing over here. So I'm going to call this the projected area ds prime, is what I'm going to call this sort of new picture frame that I've got. And the point is that it's going to be perpendicular to you, which makes it easier to actually do the calculation or come up with an argument. So the flux through this projected area ds prime is then going to be, well, what is it going to be? Well, I just need to take the size of the velocity and multiply it by this particular area. That's what it's going to be. And why is that going to be true? Because the velocity is something which is like meters per second, and this thing has an area, right? Remember, this is like a picture frame which has a certain depth that you can't see here. So this is an area, it's in meter squared. So this is going to give me meter cubed per second, right? So it's going to be the volume per unit time which flows across this. So that's exactly the correct quantity to write down. But I see something which is pretty nice here. Now, if I remember this definition that I had at the beginning of this lecture, so if I'm thinking of a vector surface element as being sort of, it's essentially the scalar one, but I assign this extra directionality to it. That's a unit vector. So here is my original picture frame. right? So with that had some depth to it as well. So I had this picture frame. So the normal vector is pointing in that direction, and the normal vector is pointing in that direction wherever we are, because it's a flat entity. So I have this. Okay, so so my n is pointing in that direction. And if I think about this just a little bit, one thing that I do know is that this area ds prime, right? So that's going to be the area associated with my picture frame over here, is going to be this, the area of this picture frame times cosine of theta, because it's just a projection. And the reason for that is because this length here is going to be, well, that length times cosine theta, and then the depth, which I can't see here, the depth which is going downwards, is going to be the same, right? So all I need to do to calculate ds prime is I need to take ds and multiply that by cosine theta if this angle is theta. Okay, something nice. If I do a little bit of construction over here, if this angle is theta, so this n is perpendicular to the pink curve, right? It's perpendicular to the pink curve. This horizontal line is perpendicular to this vertical line. So that tells me that this angle here has to be theta as well, right? So, but this horizontal line is the same direction in which u is going. So u is in that direction, right? And that tells me then, when I look at what I have over here, right? So I have a magnitude of something that's going to be the magnitude of this vector ds, and then I've got the cosine theta. That reminds me of a dot product, right? So this is purely and simply the dot product between that and that, right? And this is of course equal to ds. Okay, so what I have here, and in fact, let me write this down. So an alternative way of saying this is that this is u dot ds. Okay, so if I want to calculate the flux of a vector field, which is flowing through a tiny little element over here, what I need to do is I need to take u dot ds, and this, taking this dot product, looks at the projection in the normal direction. That's sort of what you need to do. And then so here's me highlighting this. So in general, now the earlier example was with respect to water flowing, but in general, right, if I give you just any old vector field f, then the flux of this vector field f across an infinitesimal area element ds, which has a certain direction as well, is just given by f dot ds, right? So I can write it like that, or I can write it like that. Okay, so that tells me then that if I want to find a flux across an entire surface S, what I have to do is I just have to add together all the fluxes over the infinitesimal areas, right? So I just need to add together these things. And what does that mean? Well, that means doing an integral. So this thing here is called a flux integral, right? So that's a certain type of surface integral. Okay, how do we compute this? Well, when you're trying to compute this, so the whole difficulty is this beast over here, this ds over here is the problem. But in a previous lecture, we just calculated, we figured out how to calculate ds, right? So that's actually the magnitude of it. We figured out how to calculate this, and that was by just taking this quantity over here, right? So we had a parametrized surface, we have u and v as parameters, and then my ds without the vector sign would be that thing there. Okay, all right. So what my ds with the vector sign, all I have to do is to just remove these two normalization bars, and then I actually do get a vector. I know that this is correct from the perspective of the magnitude, because if I got rid of that, I know that it's equal to that. Okay, so the norm of the right hand side is going to give me just ds, which I know that this ds vector ds, the norm of that is just a scalar ds, right? So the norm of this is going to work. But what about the direction? So the direction is ru cross rv, and that direction is always going to be pointing outwards. And the reason for that is because ru is going to be, so if I have a surface over like this, so u equals constant curves will be in one direction, and v equals constant curves will be the other direction, will be in some other direction, and at a point of intersection. So ru tells you how your location is going to change when you change u. So that will be going along one of these curves, and rv is going to tell you how your location is going to change when you change v. That will be going along the other curve, the u equals constant curve, and both of these curves are on the surface. So if you look at the tangent vectors to those curves at those points, both of those tangent vectors are on the surface. So you take the cross product between those two tangent vectors, again using the right hand rule, you have to get something which is perpendicular to the surface, because the cross product product between any two vectors is always perpendicular to both of those vectors. So that automatically gives you the correct direction. Of course, there's a little ambiguity here. Do I take RU cross RV, or do I take RV cross RU? If I take the opposite, I'm going to get a vector in the opposite direction. So here's an ambiguity when we're figuring this out. So if somebody asks you what's the flux across the surface, well, you're entitled to ask them, well, in which direction, right? So in one direction, it's going to be the negative of the other one. Okay. All right. So this then just tells us how to find ds. So all we have to do is just follow what we've done in the past, essentially, but we no longer have these normalization and these norm signs. We just take this as it is, and that gives us the appropriate vector, which is pretty neat. So once we have that, when I'm doing a flux integral f dot ds, basically what I'm able to do is I write this completely in terms of, well, f is a function of a general location r. I write that in terms of u and v, so that's easy. And then this ds, I write it in terms of u and v because I have this expression over here, and then I just reduce this to a double integral over uv. So it's over a flat space uv. So that's how we do it. So let's look at this this example over here. So let's try to find the flux of a vector field. So we're given a certain vector field crossing the part of a plane. So here's an equation of a plane which is given in the first octant, right? So just like there's a first quadrant in xy space that corresponds to where both x and y are positive, there's a first octant in xyz space that corresponding to where x, y, and z are positive. So that's the first octant. Don't ask me which one is the second octant. I don't know, but there's 8 of them, which are found by the division through the coordinate axis. Okay, so let's look at this plane here. So I know that this is the equation of a plane. So if y and z are equal to 0, I get rid of that. X is equal to 6. So that means that it goes through this point over here. If x and z are equal to 0, then y has to equal 3. So I know it goes through that. And then finally, if x and y are both equal to 0, z has to equal 2. So it goes through that. So it's a plane which I've drawn over here in the first octant. Okay, and one thing that I notice here is that this equation I can rewrite in this form as well. If I just write it as z equals some function of x and y, that's what I get over there. Now, in order to calculate this flux, what I really need to do is I need to parameterize this in terms of u and v. Well, what are u and v? Is there a good choice of u and v? Well, it turns out that in this case, well, here's a fairly straightforward choice of u and v. Why don't I just take the x coordinate to be u and the y coordinate to be v? And if I do that, then I look at the z expression, and that's going to be a u and that's going to be a v, which means I can write my z as a function of u and v as well. So my general location, I have now been able to write as in terms of this u and v, any general location on this surface. Okay, but what should uv? Can I just choose uv to be any old thing? Well, my u and v and the x and y coordinates. So if I look at what's going on down here, so the projection of this sort of triangular surface into the xy plane is itself a triangle, which I've shaded in green over here, and u and v, which are of course equal to, u is equal to x and v is equal to y. Those two things have to take on all values which lie in this green triangle. Okay, so that's what I need to do. So those are going to be my limits. So I'm going to have to write down those limits in a moment. So in order to do that, I need to know the equation of this line in the form y as a function of x, or equivalently v as a function of u. So this is easy enough to figure out. The equation in the xy plane or in the uv plane is given by this thing over here. Right, so when I'm writing down my limits for the integrals, I'll have to write down the limits corresponding to this triangle. Okay, so that's one thing that I realized. All right, so let's see. So my what do I need to do? I need to first figure out what this ds is, and in order to do that, I need to do this calculation, ru cross rv. So I need to write down r as a function of u and v, and I already know this. I figured this out. The x coordinate is u, the y coordinate is v, and the z coordinate is that, and that's what I've done here: x, y, and z. Okay, so this is what I need to do. So what I now need to do is I need to then go ahead and take these derivatives, right? So when I take the derivatives, so when I take ru, I take the u derivative of this. So the u derivative of this just gives me an I. Nothing from there, no contribution. And here I got a negative third u, so I'm going to get a negative third in the k direction. So here's my ru. That's it, right? So I next need RV. I need the V derivative of this. So V derivative of this is 0. V derivative of this is, well, it's just going to be the vector J, the unit vector J. V derivative of this, I have a negative 2/3 is what I get in the K direction. So here's my RU and here's my RV. Now what I need to do next is I need to take the cross product between RU and RV and stick it back in here. So I'm just going to do this slightly differently. Of course, I can put this in the form of a determinant and do it, but I'm going to just do it using essentially the distributive law, right? So I can write it like that. So here's my RU, which I've written over here, and my RV I've written as the second thing. And then what I need to do is I just need to take each of these individual, there's only 4 terms that I need to take here. So I cross J is equal to K. So this first thing is going to give me a K. The second computation, so I cross K is going to give me negative J. So that's going to be a negative J, but I got a negative 2/3, so I'm going to get positive 2/3 J. Okay. Now the next 2 terms are this K cross J, right? So basically what you do is you think of I, J, and K. Maybe it's worth writing this a little bit more carefully. You think of I, J, and K. Here are my unit vectors, and you just think of going in that direction, right? So if you're going in the proper direction, you're going to get a positive. So I cross J is going to be positive K. If you go J cross I, you're going in the opposite direction, so that's going to be negative K. All right, so K cross J, K cross K is going the negative direction, so I'm going to get a negative I in that case. Yeah, so I'm going to get a negative I in that case, but I've got a negative 1/3, so that's going to give me a positive 1/3 I. And then finally, I have K cross I. K cross I is equal to 0, right? Cross product of a vector with itself is equal to 0 because the angle in between them is 0. So this is what I get from RU cross RV. And in this case, because we have this nice flat surface, this is actually a constant. It's going to be exactly the same at every single location, which makes sense because the normal vector is exactly the same at every single location on this flat plane, right? So it's the same normal vector. It's actually not curved. So we're not surprised that when you take RU cross RV, we get a constant vector. So then I've got this, and now I can stick it back in here, and I know what my ds is, right? Okay, but now, what else do I need to do? I'm going to take f.ds, so I need to figure out what my f is as well. So here was the f that was given to me, but I'm writing this in terms of uv and u and v, and here are my connections between the x coordinate, x, y, and z coordinates and the uv. So I just substitute everything in here, right? So when I get x squared y, so x is equal to u, y is equal to v, so that's u squared v, and so on. So I substitute everything in. I've written f in terms of u and v, and from what I had on the previous slide, we've got ds in terms of u and v. It's this vector times du dv. And now all I need to do is I need to take the dot product between these two, right? So when I take the dot product, so that's what I've done over here. So the dot product is easy, right? So the I components, I need to multiply together the I components. So u squared v times 1/3, that gives me this term over here. Then the j components, I need to multiply that by 2/3, and I get that. And then the k component, I get that multiplied by 1, I get that. So here's what I need to do. I need to integrate this, and then I've got a du dv, which I've chosen to write in this case in the form dv du. And the reason why I'm doing that is because I need to now figure out these limits, right? So this is now a double integral in UV space. So I need to actually go all the way back and figure out what's going on here by looking at, say, let's see what's happening to U. So U is the X coordinate. So U goes from 0 to 6. Yeah, it goes from 0 to 6. That's what happens. And so my outer limit goes from 0 to 6. And then for a chosen u value, I need to figure out how my v varies. And my v goes from, well, that's v equals 0. And that's v equals this thing over here, right? So -1/2 u plus 3. So that's how I figure out what my limits have to be. So this is something which you know from doing double integrals. So you end up with this thing over here. Okay, so having got to this point, all the sort of the new material related to this this section is over here. So having got to this point, now what you need to do is just some tedious algebra, right? So you work through this in the usual way. You first have to do the v integral. So you integrate all of this with respect to v, treating u like a constant, and then you plug in these two values, and then you get a whole unholy mess over here. And then finally, you got the integral from 0 to 6 of this mess that you computed, and you integrate that with respect to du. So I'm not going to do this because I don't really care about the answer. What I really care about here is understanding the process of setting this up. So next time we'll do another example example related to a flux integral.